Hello, everyone. Yes, thank you for joining us for this MIF++ seminar. It's a great pleasure to introduce Professor Marjorie Senechal from Smith College in the US, who will talk today about ducks, crystals, and Nobel Prizes. Over to you, Marjorie, please.
Okay, thank you. Thank you. Let me start by just explaining about this talk. It's a very strange title, and the talk is very elementary. And the reason is that I did a version of this for the retired faculty here a few weeks ago, and most of them are not scientists, and so I had to make it absolutely clear with no background at all. And I was very conscious all the time as I was talking that the things I was talking about, you all know much better than I do, and that you would have a lot to say about it. And so I thought I would give you more or less the same talk, but hope that you will comment and show me where I'm making mistakes or where I could say things better, whatever, to improve this. And so I'm really grateful that you came today, and I hope that you'll find ways to help me make this better. So the title is Ducks, Crystals, and Nobel Prizes. I mean, real ducks, real crystals, and real Nobel Prizes. And the connections came about when the Nobel Prizes were announced last October, and I'll explain where. So this is the abstract, which you've all read. In 2024, the Nobel Foundation awarded its chemistry prize in part for an AI model that predicts how proteins fold. I call that a ducky solution to a vital problem, and I'll explain what I mean by ducky solution. But the question that arose right away was, has this problem really been solved, how proteins fold? And the answer to that depends on what you mean by how they fold. So we'll go into that a little bit. So this was from the New York Times. No, I'm sorry, the diagram was from the Nobel Prize. The headline was from the Times. Nobel Prize in Chemistry goes to 3 scientists for predicting and creating proteins. But this is the Nobel Prize diagram showing various amino acids. And then here they link into a chain, and then they fold up. And the question is, how do they fold up? How does a protein fold? And they were able to predict that and to create proteins that nobody had ever seen before. And that's what they got the prize for. What I can get this off here. It's just continuation of that diagram. The protein folding method was called AlphaFold. This was the AI model. And the model the AI is trained on all known amino acid sequences. That is, that all those are fed into it, and it has that in its database, and determine protein structures. And then it takes the amino acids that it's for this unknown structure and tries to compare them to the things it already has. And then it goes through various different steps to improve that and so on. I won't bother with that. But it's basically we've got all these that we know, and let's take this new one and see if it fits and matches anything there. I first heard about the protein folding problem back in 1970. So I've been aware of them for a very long time, but in a very unusual way. So I heard about it from Dorothy Rinch, who was then a lecturer in physics here at Smith College, and I was teaching math. And I got to know her very early. This is a picture of her in this car arriving at Smith in something called a Smith-mobile. Nobody at Smith has ever heard of this. And the archives don't know what it was, but somehow they put a label on here calling it a Smith-mobile and brought her to the college. And she's sitting in the back here, nicely dressed with gloves and a hat and a veil. And we don't know who took this or when, but it's in her collected papers. And here is a picture of her. This is maybe 20 years later, teaching Introduction to Molecular Biology here at Smith. It actually was the first time that such a course had ever been taught anywhere. And the term molecular biology had just been coined very, very recently. So this is what she looked like at that time. And these were some of the students in 1965, 66. In the 1930s, what had she done? Why did she tell me about the protein folding problem? She had developed her own theory of protein structure. She was a mathematician, but she was also a chemist, and she was also a biologist. She was many different things, and a pianist. And among them, she had developed her own theory of protein structure, and it was very different. So the amino acids, yes, that's the foundation of it. They link into chains. as they do in the other. But now these chains form hexagonal rings. She called those cyclols. And the rings join up to make a fabric that looks like lace. And then the fabric folds up like origami into polyhedra, which were the molecules then, as she saw it, for proteins. So what this looked like, this is her diagram of the amino acids all joined into rings. And here that's the hexagonal rings. Here's an explanation of them. We don't need to know those things right now. But anyway, here are the rings they form, and then these form hexagons themselves. So it's hexagons forming hexagons, and the whole thing forms this big fabric. And then this all folds up, and you get something like this. And this was her model of the protein. This is called the cyclone model. This is a lantern slide. It's broken. That's why you see these lines. It's just cracked glass. But this model was made for her by Niels Bohr in his laboratory. He was one of many, many famous scientists who were very impressed with her ideas. And part of the reason that people were so impressed with her ideas was that she was able to answer experimental questions. So there were two pieces of evidence at the time, both of which have been discounted now and not true. But at the time, they were believed very seriously. One was that protein molecules belong to just a few weight classes. So before people realized that proteins were molecules, they thought there was just a bunch of amino acids in a pack. Then, when they realized that they were molecules, there had to be a structure. And the first evidence seemed to suggest that there were just a few weight classes. And her model fit that perfectly because she could make little polyhedra, bigger ones, bigger ones, bigger ones. But they all had the same sort of basic structure with triangular faces. That was the same polyhedra and the different sizes. Amount of acids couldn't make them with any given number. It had to be those that fit into this triangular pattern. And another thing that was considered very important was that the number of amino acid residues in every protein is the product of powers of 2 and 3. This was the Bergman-Niemann formula, and people thought that that was the real key to understanding protein structure. Turned out to be completely false, but at the time, that was the question to answer, and she could answer that because the numbers could be counted and calculated for all these different sizes. But the problem with her model was that it required a chemical bond to make these things fold up and do things that some thought couldn't and didn't and couldn't exist. So she was very controversial. She was in the papers. This was I found in the Rockefeller Foundation archives. Woman Einstein, Dr. Rinch solves biological problems mathematically. And here I've quoted just two of these. It's a wonderfully interesting article, but it would take us all day to read it. So what's important, she's the fulcrum of an exciting battle in science. She believes she's taken the first steps toward discovering the secrets of the structure of protein molecules. Other great scientists agree with her. Others are great. So she's great and others are great. Others poo-poo it. And so there was quite a battle. She said, exciting battle in science. And who was the opposition was led by Linus Pauling. And this is an interesting piece of paper here because it's from his archives. There's a website called Linus Pauling Day by Day, and every day of his life is cataloged here. And this particular day, January 26, 1938, when he met with Dorothy Ridge, and they discussed all this in detail. And he took notes, and then he gave her the notes to make comments on, which she did in pencil. All these are hers in pencil, and they fully disagreed, and they never came to agree. So but I thought it was interesting that they did have that long discussion and wrote it out, and that he graciously let her make comments on his notes, so that both points of view are are represented here. But Linus laughed Dorothy out of the field. He just thought it was hilarious, and that she was hilarious, and he essentially marginalized her, put it mildly. And with his 2 Nobel Prizes, he had a lot of say. But one thing I think they would agree on today is that the protein folding solution is incomplete, that this has not really been, not fully solved. It's been partially solved, but not fully, even though it got a Nobel Prize. So I want to back up just a little bit. How could they know what the structure of a folded protein was? And you all know this stuff very well, but let me just go over it. So in the years before AI, the way they knew they could know was, first of all, was to crystallize the protein and then try to deduce the structure from the crystal. So that was the first direction, best thing to do. And that was quite a job, as you know. And so that takes us back to 1895, when Wilhelm Conrad Röntgen discovered X-rays. And he called them X-rays. The X was his idea, and that was because he didn't know what they were. And so the X stood for the unknown. He had that much of a mathematician's intuition. And this is then from the Nobel Prize website now. Says the reaction to Röntgen's X-rays made him an instant celebrity. Many honors were bestowed upon him, streets were named after him, and Röntgen received countless honorary doctorates and prizes, including the first Nobel Prize for Physics in 1901 for his discovery of the remarkable rays. And they took pictures of everything they could. This is a picture of his wife's hand with her ring. You can see her ring here. And she looked at that and said, "I've seen my death." She was really, it was quite a dramatic event to see this, but it revolutionized not only science, but medicine too, because now if somebody had a broken bone, you could see where it was broken and you could try to, you could bind it up and heal it or operate it, whatever you needed to do, whereas before it was a total black box, literally. So that was the discovery of X-rays. And then the other thing that came into play here was the long established theory that crystals were orderly stacks of molecules of some sort. And this was Aui's drawing of crystal shapes. This would be the, you can see what they are. He's got them here, this, and so forth. But how they could be all approximated by by little bricks, which he called molecules, all stacked in some sort of periodic order. And so mineralogists had long conjectured that all crystals were orderly stacks of some sort. And we can't see the atoms in a crystal by X-raying it like a hand. They're too small. But it was understood that if the stacking theory of crystal structure is right, and if X-rays are waves of the right wavelength, then a crystal will scatter the X-rays. So we can use X-rays to understand how the atoms are arranged because we can look at the scattering patterns. So something like this. If you have an orderly pattern like this, you get a diffraction pattern, something like this. This is a bent sheet. I'm sorry about that. But anyway, it has sharp, bright spots. So orderly and sharp, bright spots go together. Disorderly and sort of foggy go together. And so that was the reason why X-ray diffraction was going to be helpful in determining crystal structure. And Max von Laue solved for the X and X-ray in that way. And he received the Nobel Prize in Physics in 1914. And this is a picture of how that works. So here are the incident beams of the X-rays coming and striking the atoms in the crystal. This is as they're assumed to be arranged. And then they scatter off. And this goes to a photographic plate. And here's a picture of this. And you see the sharp, bright spots. And so this is the 1914 Nobel Prize for. And as the Nobel Prize Foundation says now, as a result of von Laue's discovery, the diffraction of X-rays and crystals, proof was thus established that these are light waves of a very small wavelength. However, the discovery also resulted in the important discoveries in the field of crystallography. It's now possible to determine the position in crystals, and much important knowledge has been gained in this connection. And if there's permitted to evaluate human discovery according to the fruits which it bears, there are not many discoveries ranking on a par with that made by von Laue. And then just at the same time, as soon as he announced that, then the Braggs started using this and deducing the structure of several crystals right away, including table salt, which you now see this in every chemistry lab in the world. This was a shock. It's hard for us to realize today that this was a shock, but it was a shock because people thought there would be molecules. So there would be sodium chloride molecules somehow arranged. But the way this is arranged, and everybody had to realize this is the way it's arranged, it's a checkerboard, and you can't associate one and one. Each one is surrounded by 6 others, and that's that. And so there are no molecules in here, and that was a big, big surprise. And anyway, that helped them to get the Nobel Prize in 1915. And then just to mention, then this went on developing all these ideas for more and more fully and more detail. And Dorothy Wrench stayed in the game. And she wrote a nice little book on Fourier transforms and structure factors, which actually, even though people thought she was crazy, they received it. This was very well received. And so she got back her position in the field. And then, as we all know, in 1962, the Nobel Prize in Chemistry went to John Kendrew and Max Perutz for their structure model of the first protein, myoglobin. And what they had done was to crystallize it. It took forever. Finally, they were able to do that. Then they did all this X-ray diffraction, just as we saw, and came up with a structure, which is hard to fathom from the pictures, but Anyway, it was quite a success at the time, and it was correct. And this was 50 years after Bragg had first deduced the structure of table salt, 62 years before Baker, Hasselbeis, and Jumper won the Nobel Prizes last year. They were right smack in the middle of that. So this is a diagram, I forgot what, from Quantum magazine, explaining how excuse me, let's go back. Whoops. Backwards. Yeah, explaining how X-ray diffraction crystallography works. And the reason I want to put it in here is because this is the modern view of it rather than what I just showed you. So here it says purified proteins in solution are grown into a crystal. That's the same thing. Locking the structures into a fixed pattern. And this could take years of trial and error. Now, protein crystal is bombarded with X-rays from many angles. A detector determines the diffraction pattern of scattering. There's no more photographic plates. The photograph and the film, and those are all gone. But now that you have a detector, the detector then builds up the structure, the electron density map, and then they're able to construct the protein from that. So it's much more automated, but this is still the same procedure. The steps in it are much more automated. And that's considering what struck me about this was that they used the past tense here. This is what structural biologists used to do up until a couple of years ago when AI came into the picture. So now we have protein data banks, which, and I just thought it was interesting to see the difference here. The structure is determined that in the way that I just explained, there were 232,059, and then the computed structures with AlphaFold, it's way over more than 5 times that. So it's rapidly, then this is already out of date, even though it's only a few months old. So as you know, this is just changing as we speak. So how does the string of amino acids fold up? Has it been solved? And as I said in the abstract, this depends on what you mean by how. The answer is yes, if we want to know what the folded string looks like. We can do that. That's what that does. But if we want to know why it folds the way it does, what's the chemistry going on here? What's the physics? What's happening here? That is not anywhere in that solution. This is an article I found from Harvard. I think this is Harvard Medicine or something. But anyway, with the question, did AI solve the protein folding problem? And 2 scientists whose names I can't pronounce, they say have already started peeking into the inner workings of OpenFold, examining the shapes of the structures it builds during its training to find out how it learns. What they found is a bit bizarre. For instance, instead of following the steps of folding as they happen in nature, which is what people were trying to find out, or the earlier people, the model starts by creating one-dimensional views of folded proteins, followed by 2- and 3-dimensional views. The model doesn't necessarily need to know the basic physics to do its job of piecing together the protein structures. But the scientists argue that the more the physical knowledge is infused back into the deep learning systems, the better they'll work, and better we'll understand how they work. But there's still a long way to go to understand how this really happens in terms of the steps of the at the atomic level. And now we get the ducks. So how are we doing on time? Okay. So now the ducks waddle into the story. And they waddle in with Dan Sheckman's discovery of a tenfold diffraction pattern in 1982. And so this is, I listen, this is the theorem. It's never usually stated as a theorem. It's usually called the crystallographic restriction and is more general, but this will do for this. This diffraction pattern here with tenfold symmetry, bright spots, tenfold symmetry is impossible for any periodic stack of atoms, and that's easy to prove. So this picture does not fit with whatever this is, but this is still bright spots. So what's going on? So if bright spots mean orderly arrangement, then what kind of order is this? Is this not this kind of order? It's not translational symmetry. So what could it be? And so this opened up this whole new world. Here are 2 examples of other kinds of order, which are related but not identical. This is Roger Penrose here in 2023 at the Hat Fest that was celebrated at Oxford. But he's standing in the courtyard of the Math Institute at Oxford, and it's paved with the Penrose pattern, Penrose tiling pattern. So here, if you look at the floor instead of at Roger, you'll see the Penrose tiling, and you'll see one of the kinds of order that is not periodic, but is still very orderly. And then here, this is the first crystal structure to be determined, aperiodic crystal to be determined at the atomic level. And this is various overlapping polyhedra with with pentagonal symmetries. And so it was quite a discovery, and this was in 2007. It took all that time from 1982 to 2007 to determine the structure of a single one of these. But this was what it looked like, and how they modeled it. And then, as you know, Dan Shechtman won the Nobel Prize in Chemistry in 2011. And the Nobel Prize Foundation said that the prize has fundamentally altered how chemists conceive of solid matter. So a real revolution. I think it's a little odd English to say the prize did it. It wasn't the prize, it was the discovery that did it. But nevertheless, this is what I have to give an exact quote, what they said. So this leads to what I call the duck definition of a crystal. So the realization that I'm quoting this from, again, the Nobel website, this realization that there are structures that are orderly but not periodic led the International Union of Crystallography to alter its definition of what a crystal is. There was a commission on nomenclature, and one of them was charged with finding a better definition of crystal that fit contemporary understanding of crystal, which is quite different. I was on that committee, and I argued very hard for this position. So we said previously a crystal had been defined as a substance in which the constituent atoms, molecules, or regularly three-dimensional, and then if it's bright spots, it's a crystal. That's it. This definition, they say, is broader and allows for possible future discoveries of other kinds of crystals. And there's the ducks. And so this comes from the saying that if it walks like a duck and quacks like a duck, it's a duck. And that's what I call the duck definition of a crystal. If it's got bright spots, it's a duck. And that was adopted by the International Union, and the Nobel Prize people like it a lot. And they continue saying this, and I'll read. This may be hard for you to read because it's a little blurred, but I couldn't get a better picture, so I'll read it to you. This is still the Nobel Foundation. While formal definitions may be more or less important to science, this one, the duck definition, is interesting because it makes no attempt to define the concept of crystal directly, but rather provides an operative definition based on the diffraction pattern of the material. By crystal is meant any solid having an essentially discrete diffraction diagram. The discovery of quasicrystals has taught us humility. As pointed out in a recent review, we do not know when the next class of non-periodic exciting crystal structures will be discovered, or if there will be such a discovery at all, end quote. Rather than making mistake, this is Nobel again, rather than making the mistake of again being overly restrictive, science now treats exclusive statements about long-range order with caution. So that was the legacy of the quasicrystal discovery, was to generalize to make the definition of crystal operative in that sense that it's a diffraction pattern that matters and not the structure. It doesn't mean the structure is not important and that you shouldn't try to find the structures. And of course, you have to understand the structure if you're going to use any of these materials. But this is to say, what is the definition of crystal? And to my surprise, this was not welcomed by crystallographers very much. Although it was passed, it was not welcome. And so if you look at the online dictionary of crystal, this is after many negotiations and much discussion. I've been in on some of that, but not all. And they finally decided to give two definitions. One is direct space definition, which is what people wanted. A solid is a crystal of its atoms, ions, or molecules form on average a long-range ordered arrangement, whatever that means. And then it goes on to say, in most crystals, the arrangement is a periodic array that's governed by the rules of translational symmetry. That's the classical kind. In aperiodic crystals, commensurate or quasi-crystals, the arrangement is not periodic in 3 dimensions, but is nevertheless still fully ordered and then says where the ordering follows particular mathematical rules. Now, the odd thing about this, if you look closely, it says particular rules, but doesn't say what those rules are. And one reason is because we don't know what they are. We know some, like with the Penrose tilings and with some of the others, but there may be others that we don't know. And so the definition allows for any crystal if the atoms, if you have a sharp diffraction pattern, but what particular rules that follows is still to be discovered. But it's still their problem. It's not to be ignored. It's just that we don't know. This is a little too optimistic. Then the second definition had voted happier with this one for the very same reason. I think that people are a little uncomfortable with saying that the AI has solved the problem of protein folding, because it's really very similar to this kind of definition. So I say, this is my point of this talk, is that AlphaFold 2, which they was awarded the prize, is a ducky solution. It's really saying if it looks like what we've got here, then that's what we've got, and it's not exactly that, but it's close enough that it's really sort of a matching of this is what we see, this is what we have over here. We match these, this looks together, we call it, we quack. It's a quack, it's a duck, it's a protein, and so on. So look, if you compare that with the discussions, all the discussions about quasi-crystals and crystals and what is a crystal, and then there is a similarity in spirit, or at least in philosophy, that the duck definition is valid and works for parts. So I wrote a biography of Dorothy Rich and then some blogs for OUP. And this is one comment that I think still holds. The structures of that time I wrote thousands, today it's hundreds of thousands of proteins are now known in exact detail. Their inner logic, which is where's the chemistry and where's the physics, remains where Dorothy left it, a brass ring on the Nobel carousel. It's still to be there, and it's still a problem. And it's just a great problem, but it's still a problem. So that brings me to just a few comments at the end. Vital, how much time do we have?
Marjorie, you could easily have 15, 20 more minutes, so no rush.
Okay, well, this is very short. Then we just have a discussion. That would be good. So just a few things I just want to add, which I didn't. Okay, these are some comments that I especially prepared for the Emeriti that I gave a similar talk to recently, as I told you, of how all of this is so pervasive, of the AI and the doctor, and it's so pervasive, and it's all happening every day. I mean, I look at the newspaper every day. There's a new whole big chapter in this, and I'm doing my best to keep up, but I certainly don't know half of what's going on. This appeared just recently in the current IUCR newsletter, which this is something you all know about and are working to try to improve. These days, the availability of machines that appear to solve crystal structures automatically and the lack of basic knowledge of crystallography means that false structures are sometimes accepted and published. And this is a big problem across the board, and many things, interesting approaches are being taken to try to reduce that, and you know those better than I do. Another comment, I thought this is a case where the duck solution is actually is really helpful. This was, there are many medicines that have been developed over the past 50 years, which in the United States, which received approval from the Food and Drug Administration. They're perfectly legal. There's nothing fake or mysterious about any of them, but they just never became widely known, and yet they worked, and they were forgotten. And so many diseases that could have been cured in individuals were not, because they didn't know about these particular medicines. Now with AI, they can they can have the databases are enormous, and they can search them instantaneously for various different symptoms and processes, and able to bring out drugs that have been there all the time, but nobody knew about, and use them to save lives. And it's a very interesting story of how the scientists are using machine learning to find new treatments among thousands of old medicines. This is there are other things like this happening too, where just the ability to have this vast data and to be able to sift it instantly is fantastic. This is another thing that's happening, is concerns about copyright. This is a book of poetry by a friend of mine who teaches here at Smith. And in the first page of the book, it says, no generative AI training use. Publisher and author grant no rights for use of this work in any training of artificial intelligence technology to generate text and so on. This is now, I think, being put in almost every book because issues and whatever other concerns people have. And I think this is what the basis of the New York Times lawsuits against Microsoft and against DeepMind and so on is using culling all this material from the web and using it for AI training use, and then it's gone. It's vanished into the the common use. And so I asked my friend about how she arrived at this decision to do it. She didn't even realize that they'd done it. The publisher put this in without asking her. So it says publisher and author, but she didn't know that she was part of this. But she agrees, so everything's okay. And then I'm almost finished here. This is from Quanta. It says artificial intelligence can clearly advance specific kinds of scientific questions, but it may get scientists only so far in advancing knowledge. Historically, science has been about understanding nature, and this is one of the people I was quoting before in the Harvard piece. The processes that underlie life in the universe. If science moves forward with deep learning tools that reveal solutions, but no process, is it really science? And this is a question. I mean, is science going to change? And in what ways? And how is science teaching and education going to change? There's more questions than answers here. Also, there's concerns, as you all know, of this being misused or taking over other things that it shouldn't. And so this was just a picture of Geoffrey Hinton. This was a couple of years ago from The Guardian. And it says here, the man often touted as the godfather of AI has quit Google, citing concerns over the flood of misinformation, possibility for AI to upend the job market, the existential risks posed by the creation of a true digital intelligence. Dr. Hinton, 75, said he quit to speak freely about the dangers of AI and in part to regrets his contribution to the field. He was brought on by Google a decade ago to help develop the company's AI technology, and the approach he pioneered led the way for current systems such as ChatGPT. I don't know if you all realize, so anyway, he received the Nobel Prize in Physics in 2024. That's exactly the same time as the other one for the AI AlphaFold. I don't know if you know what an interesting family he comes from. Geoffrey Hinton is the great-grandson or great-great-grandson of George Boole, who was the founder of modern logic. But there are many more also other interesting people in the family, including a great aunt of his who wrote a famous book called The Gadfly, which was made into operas and ballets, and it's still read around the world. So she was a famous writer. Then there were scientists in the field. There were it's a lot, but one of them I particularly wanted to mention to you was a cousin of his named Joan Hinton. And Joan Hinton was a nuclear physicist who worked on the Manhattan Project at the time of the Second World War. And she was so appalled. So it's very similar to his position. So she worked on that. Then after the war, when she saw how physics and nuclear physics was being militarized and becoming part of the military structure, she decided she had to quit. And just as her cousin later did quit Google, she quit physics altogether, and she moved to China. And she became a dairy farmer, and she developed new kinds of milking machines, and she had her own farms, and she was very famous. And there in China for her, not as a physicist, but as a dairy farmer. And when I was visiting China in 2010, I asked if I could visit her, and everybody knew her. They said, of course, of course, of course. Then they called her up. She said, sure. So I went out with a graduate student, drove me out, and we spent the day in the dairy barns and talking to her about her life and work. And it was very, very interesting. And sadly, she died shortly after that. But this is a picture of Mao Zedong in the background in her. This is the living room of her house. But she was a very interesting person and interested in all her relatives that I knew about. And we had a lovely day. But I think of them as both equally courageous to leave the field that they had to which they contributed so much because they were concerned about the principles of what was going to become of it. Then I'll conclude with this. This is just a little clipping from the paper the other day, March 14th, by Kevin Roos, talking about basically how this is changing everything, artificial intelligence. Most of the advice, ducks, I would say, most of the advice I've heard for how institutions should prepare for artificial general intelligence boils down to things we should be doing anyway, he says. Modernizing our energy infrastructure, hardening our cybersecurity defenses, speeding up the approval pipeline for AI-designed drugs, writing regulations to prevent the most serious AI harms, teaching AI literacy in schools, and prioritizing social and emotional development over soon-to-be obsolete technical skills. These are all sensible ideas with or without AGI. I wonder what he means soon-to-be obsolete technical skills. It could be reading, writing, and arithmetic, as far as I can see. Because kids are not learning to write script anymore. Nobody learns arithmetic when they've got hand calculators. And even reading, I gather, is in danger too. So there's a lot to worry about and to be concerned about here. I think he's a little bit too positive here about sensible ideas. They all need consideration. And so I close with this. That's it.
Thank you very much, Marjorie. Could you please keep your slides? Because we might have questions.
Oh, okay. Let me put them back up.
Thank you.
Let's
Yes.
see. I don't know if I can get them up again.
So share screen and then window.
I've got share screen.
And then while you're doing, let us first thank Marjorie for the beautiful presentation.
You don't have to.
So physically.
I can't see. I don't know how to get them back up. It should be this one.
Yes.
Yeah, screen sharing, and now, but I can't see the. I can't
previous slide.
All right, I have to click to exit. Okay, now.
Yes.
Now I can play from the start.
Thank you. Okay, I'll stop the recording.